Welcome back to Multigrid Methods. We're in the second slide deck of Chapter 9, talking about additive preconditioners based on subspace decompositions. We already started this slide deck, but I did make a few changes, and I want to go over those kind of carefully because I think it makes the presentation a lot more readable, but it's, some slight differences. The other thing I want to say about this chapter is that this is probably the most complicated of all the analysis that we're doing up until this point. And so I'll be quite honest with you, even I may fumble across some of these estimates. And so if you have any questions, please stop me and ask questions. You can ask with your voice or via chat, and if you don't want your image shared on the video. But there are a lot of complicated issues in the analysis, and so uh, it might take a little bit of thought or a calculation on the side to get it. Um, so I'll tell you where some challenges may be, and so we can either go through them together or we can just agree that they could be done by hand calculations later. So I have an ambitious idea, and that is to get through all of this section on the hierarchical basis preconditioner, and then so we can talk in the end about whether or not we want to meet in the final lecture to go over the BPX preconditioner, or if we just want to save that for next time. So this is, technically speaking, the last lecture of the semester, class number 28, and so there's no real great pressing need or urge to meet in the final exam time to talk about the BPX preconditioner, but we could do so if somebody's really, really excited about it. All right, so hierarchical basis preconditioner, we already started talking about this, and so I want to uh, basically go through the changes that I made, and then some of the other things we won't really talk too much about. So we introduced these matrices called the Q matrices last time, and these were basically a way of mapping the basis functions from this basis, okay, so this W space basis, to the basis functions of the standard Lagrange nodal interpolation basis function, or standard Lagrange nodal basis function, BLV. So these were those coefficients involved in expanding this guy in these basis elements. That's how we define these Q JL entries. And so the QJL matrix is just that matrix which has those entries. And so again, this is a way of mapping. So if you like, the idea is if I have an element from space J, when I do this multiplication, I'm going to get a new vector. And let's see, this guy has see, make sure I got this correct here. I think I may have forgotten to correct this, right? So this guy here, we want to multiply this by a vector here and get in the larger space. So I think I forgot to permute these two entries here. I mentioned that you should do that last time, but I failed to fix that in this set of notes. So these two indices should be swapped. The idea is that we want this Q matrix to be a tall and skinny matrix, and the way I have it written here, it's not. But if you fix it by swapping these two elements, you get it. So now we have K being the row index, and there are a large number of rows and only a few columns. Okay, so that's what I want. I want to want to fix this typo here. It's fixed in the notes already, but I believe that I forgot to do that. Well, it's obvious that I forgot to do it in the lecture notes, the slides. So if I start out with a vector wj, this guy is a short vector. It's an rmj. And if I multiply q times this, I'm going to get vector w in, let's say, do I want to call it, maybe call it wl. And this guy is now in r and l. Okay, so this we can view as the coordinates of some wj function in the wj space. And the connection here is going to be the bjw basis. And that's going to get mapped to this coordinate vector, wl, and this coordinate vector is wl, and this guy lives in space rnl. I should have said over here, this guy lives in space rmj. And this guy is the coordinate vector for wl in the space vl. And the basis that we're using for that is blv. Now, the idea here is that we already know that wj, it's a subspace of vl as long as j is a lesser index than l. That's according to our construction. So we know that this object here, which originally started out in this space, is actually also in this space. So we can use the basis, the most standard basis of that space, called BLV, to find out the coordinates of that guy in that space with respect to that new basis. So how do we get the coordinates knowing that we had these coordinates here? Well, the answer is what you do is you simply multiply by that Q matrix. So it's like a prolongation matrix, and it's what we call the hierarchical prolongation matrix. So we've already introduced this concept, but as I said, I forgot to fix this typo, and I just wanted to remind you what's going on here. All right, so the rank of these matrices are all full. And as I just said, if we want to get the coordinates of this finite element function with respect to the space VL, this is a typo here as well. So this shouldn't be a vector. This should just be a function. So there's a typo there. Right, so the idea is we only put a boldface, we only put bold or put an arrow above something if it's in the coordinate space. Here, it's actually in the finite element space. So if you want the coordinate vector of this guy in this basis, then simply multiply by the Q matrix. That's what the Q matrix is doing. Now, this is where I made a major change. And before I defined these C matrices as B matrices, that was getting confusing. So now in this whole chapter, I've decided to use the notation C for a preconditioner. So I told you previously that if you have a general linear iterative scheme, then there's something called the iterator matrix. You guys remember that? So there's something called the iterator matrix. And that is that matrix which appears in this position here. That's called the iterator matrix. Now, iterator matrices and preconditioners are more or less cousins. They're related objects. So oftentimes people will use they'll use B and C interchangeably for either a preconditioner or an iterator matrix. Iterator matrices and preconditioners are closely related objects and things. They're intimately connected to each other. And so previously I was getting a little bit I was confusing you guys by using B and C both in the same chapter. So now I've standardized this in chapter 9. I'm only using the notation C for preconditioner matrix, and I'm relegating B to be the iterator matrix. So even though they're really highly related and the same, I'm using different notation for them. All right, so the other thing I did is I changed this so this was previously called B sub j. Now I'm calling it CJ, but I'm introducing it rather so instead of introducing it as a functional on a finite dimensional space, I'm introducing it as a bilinear form. This makes a lot more sense. It's a lot easier for people because you may not have seen functionals before, but most all of you know what a bilinear form is because an inner product is just a special type of bilinear form. So you've seen these. All right, so a bilinear form takes um, a pair of functions and it combines them together to give a real number. So for example, a very common bilinear form would be one which takes two functions and integrates over a domain the product of those two functions. Okay, so that's a very common one. That's called the L2 inner product or L2 bilinear form. So this bilinear form, we're taking two objects from the space Wj and we're going to combine them in the following way. So in case you've forgotten, Wj is that's that weird finite element space where every other degree of freedom is kind of canceled out. So it might look, a typical function from that space might look like that. So the way you determine these functions is you look at your typical nodal set, and every other one, those are the nodes that appeared in the coarse mesh. And so we're going to zero out or nullify the degrees of freedom for those nodes associated to the coarse mesh, and we're only going to allow them to have degrees of freedom for the nodes that were just added into the mesh upon refinement. Okay, so these are what the functions wj look like, for example. And so what we're going to do is we're going to take two functions and we're going to simply multiply them together at the nodal points where they're non-zero. That's those four nodal points in this case, where they're not identically zero, and then we're going to sum those up. So in general, the way this looks in 1D and 2D is there are MJ nodes where the function is not identically zero, and so we're going to sum over those nodes. All right, so now let BJW be the usual basis for WJ. So these functions are just those functions that are 1 at the new nodes and 0 at every other node. Okay, so these guys look like this, right? They're all just 1 functions. They're 1 at the nodes in WJ and they're 0 everywhere else. Okay, well, so that's our usual basis for WJ. Now we're going to define the matrix form of this guy. So every bilinear form gives rise to a matrix, as we'll see in a moment. It just depends on what basis you're going to use for these spaces. So I'm going to use the standard basis for those spaces. And the way I'm going to define the matrix version of this guy is I'm just going to plug in, for these two entries, I'm going to plug in phi ji and phi jk, right? So that's going to give me the element in the ith row and the kth column. right? So that's going to define the elements of a matrix. What are those elements? Well, it's not too hard to see that when you plug in these guys and then use this formula, these two functions are equal to 1 at particular nodes and 0 at all other nodes. So the way we express that is as saying this is just equal to the Kronecker delta symbol d or delta IR. And this one is the Kronecker delta symbol delta KR. Okay? Well, if I multiply those two functions together and sum over R, then what I get is just delta IK. So that's just a very simple little exercise that you can show yourself. So this very trivially is just equal to the identity matrix. And it's the identity matrix of size, let's see, it's Cj is equal to Ij, or maybe Imj, and that's equal to the identity matrix of size Mj by Mj. Okay. Now the reason I didn't put a subscript j here is because that means something slightly different. But this is essentially just the identity matrix. Now, remember, we're thinking that nj is a small number and nl is a large number. So this is kind of a smallish square matrix. Now, quite trivially, this matrix, each one of these matrices is symmetric positive definite. So it's clearly symmetric and it's positive definite because all of its eigenvalues are exactly equal to 1. Okay? So let me check chat here, I think. Okay. All right. So now we're going to define the hierarchical basis preconditioner. I think I defined this one last time as well, but again, we're using modified notation. Suppose that BLV is the usual Lagrange nodal basis for VL. So because there's multiple bases floating around, we decided to introduce this superscript V and the superscript W for the associated the basis associated to the W spaces. Let AL be the SPD matrix defined by this object. So this is the standard stiffness matrix for the finite element. So this is nothing but the stiffness matrix for the finite element method. So that's no mystery. Well, so, and by the way, this is exactly how it's always been defined. You just put the basis elements in this bilinear form A, where A is the bilinear form that's associated to the weak formulation of the Poisson equation, and that's how you get the stiffness matrix out. The hierarchical basis preconditioner for AL is defined as CH equals the sum L equals 0 to capital L, QLL, CL inverse. Now, what is the CL inverse? That's just the matrix we defined a moment ago in equation 2. That guy's just equal to the identity matrix, because if I take the inverse of the identity matrix, I just get the identity matrix. So this is just going to end up being QLL ZLL by definition, once I've defined these guys. And of course, the ZLL is just QLL transpose. Okay, so why did I introduce a new letter there when I could have just used transpose? Well, it got a little bit cumbersome because this already has one superscript, and so the transpose would have been another superscript. So, but that's the hierarchical basis preconditioner for AL in a nutshell. And now notice that it's an additive preconditioner or an additive iterator matrix. And the reason is because it can be broken into a sum of matrices. And very simply. So CH is just equal to Q 0L Z0L plus Q1L Z1L plus dot 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 all the way up to QLL ZLL. So it can be decomposed as a sum of matrices, and that's what we call an additive preconditioner or an additive iterator matrix. As long as they can be added together, then it's additive. Remember, that's in contrast to something we called a multiplicative preconditioner or a multiplicative iterator matrix because that has a very, very complicated structure. Additive is much simpler, and therefore it's much, much easier to apply an additive preconditioner. Okay, so now that we've got this thing fully defined, and I think we didn't get any further than this last time, so this is basically new stuff. What we want to show is that any vector UL can be decomposed into WL via this type of decomposition. And if that's the case, then we say that the that assumption SS1 holds, or we have what's called a subspace decomposition of the space. So here's the idea. Suppose that we have UL and VL, and so that's the finite element function in the standard space, and it's always connected to its coordinate vector via a basis. And so the basis that we had ought to use for this space is the common one, BLV. Then there exists unique objects. Either I can view these objects via their coordinates or as finite element functions in these spaces WL. Remember, WL is that weird space which has every other degree of freedom sort of punched out. In 2D, it's the same sort of definition. It's just their functions are a bit more complicated to visualize. So the way we defined it in the first slide deck, it should be clear that that it's the definition holds in 1 dimension, 2 dimensions, and even 3 dimensions. All right, so there have to exist these unique objects, or at least objects. They don't have to be unique. But in this case, with the hierarchical basis, they are unique because we're using a basis to construct them. There exist these objects WL, and we can again view these either in the finite element space or via their coordinates in the usual basis BLW, such that U can be written as the sum of these WLs via this prolongation matrix QLL, or we can view the function UL, I'm missing an L here, so there's a typo. Should be an L. That's because we had an L here, so why not bring it down to here? It should be there as well. All right, so we can write this in one of two ways, and they're entirely equivalent. So either we can write the coordinate vector UL in this way, or we can write the function UL as a sum of the WLs. And we showed in the first slide deck that it's easy actually to do this. So there, in fact, we had a formula for this, which said that WL was equal to ILV, or sorry, in this case it's U, minus IL minus 1 UL. Okay, so where these are the Lagrange nodal interpolants into the spaces VL and VL minus 1 respectively. So we actually know how to make this decomposition work, how to drive that. So what's different here is that we also can say what the coordinate vectors look like as well. And so the coordinate vectors are connected via these matrices that we introduced earlier called the prolongation matrices, or the hierarchical prolongation matrices. Okay, so that's a result, and it may not be clear, but It's based on lemmas and properties that we established in the previous slide deck. In fact, all the details are basically done for us. You just have to gather them together in bits and pieces and then stitch this function back together. And so I'm going to leave those details for a future exercise. Now, our goal is to show, remember, we're interested in using preconditioners. And so the idea of a preconditioner is when we multiply this times the matrix A, what we want to show is that the new product matrix has a small condition number. Now, the condition number can always be defined as long as we're dealing with symmetric positive definite matrices. We can always define the condition number as simply being the ratio of the maximum eigenvalue over the minimum eigenvalue. So what do I mean? I mean that it's the maximum of this eigenvalue of CH times AL, because this is now the preconditioner for this matrix. So I'm interested in the product matrix, and I want to show that the product matrix has a small condition number. Okay, so we can define it like that. And what I'm going to prove is that the minimum eigenvalue is greater than that estimate, and the maximum is less than a simple constant. Okay? The maximum is less than a simple constant. The minimum is greater than a constant times 1 plus log HL squared to the minus 1 power. Now, if I write this quotient, then I can prove, if I can prove these two properties, that the condition number is less than C2 over C1 times this weird thing here, this thing involving a logarithm. Okay, so no inverse here, just straight number there. It's easy to show that once I know that these two facts hold. So that's the goal of the rest of this section. And that's going to occupy all of those slides as long as I stop chatting so much and get into it. Now, this estimate is pretty useful, even though it maybe doesn't look useful. We've said in the past, what we really want to show is that we have a condition number which no longer depends on H. This condition number does depend on H. However, it's not a very bad condition number. And that's because this number is not going to grow all that rapidly. And you can see that just by making a back of the envelope calculation. For example, we can suppose that HL is equal to 1 over 2 to the L power. You could also argue that it's HL maybe is some H0 over 2 to the L. It doesn't really matter whether this H0 is 1 or some constant. Now, if this is true, then you can just calculate log of HL. So and of course we want to take the absolute value and then square that. Well, what is log of HL? This works out to be, when I square the absolute value of that number, L squared log of 1/2 squared. So the log of 1/2 squared, don't really care what that is. Doesn't, it's just some finite number. Doesn't change with L. Now, how does HL change? HL only changes as L becomes larger and larger. This guy becomes smaller, clearly. So that means the condition number is going to rise like the square of L. But what is L? L might be 10, right? Or at the worst, or maybe 11 or 12. So that's the number of levels that we have in our mesh. And well, if that's true, then this is on the order of 100, right? So 10 squared. That's not too bad, actually. And of course, it's not exactly that, because log of 1/2 is some number. But the rest of it is roughly, 1 plus 100, say 101. That's not too bad at all. A condition number of 100 isn't bad compared to the condition number of a stiffness matrix. If I looked at the condition number of the original AL, that's going like HL to the minus 2 power. And so that's a whole lot larger, okay, than L. And so I've reduced my condition number by quite a lot by using this estimate. And that means that if I apply the conjugate gradient method with this preconditioner, then I'm going to get a pretty rapid convergence. Not nearly as rapid as multigrid, which is what we did earlier, but and where multigrid is a multiplicative standalone operator. But the nice thing about this is because this C is an additive preconditioner, we can parallelize that. So we can throw this part on one processor and this part on another processor. And so it turns out additive is good because of parallelism. Multiplicative is still okay, but it's not quite as advantageous as an additive method because I can't parallelize it as easily, or maybe not at all. All right, now to prove that those estimates, so it's estimate 1 and estimate 2, and they're both painful estimates. I can't lie to you. They're both pretty painful, and just this is probably the hardest analysis that we've done so far or will do in the book. So we need a lot of technical details to get through this. So one of the details that we may or may not need is what's called the mean zero point Gray inequality, and it goes like this. Suppose that omega is an open polyhedral domain, then for every u in h1 omega, u minus u bar L2 is less than a constant times the L2 norm of the gradient of u. What is u bar? U bar is what we call the average, and it's taken over the whole domain omega. Okay, so that's the average value. So this means the measure of omega. So if it's a square, 1 by 1 square, say, then this is just the area of that square, which is just equal to 1. So why do I need the average there in the first place? Well, it's necessary because let's say u is just equal to a constant function. Say it's just equal to 1. If I don't have this guy there, and u is just equal to 1, then the L2 norm of the function 1 is non-zero. But what about the gradient of u? If the function u is just equal to 1, then the gradient of u is just equal to 0. And there's no way that the 0 can control this guy. Now, what I need to do is put this guy back in there, this average, and then I can show that the L2 norm of the difference between u and its average is controlled by this this function or this norm. Okay, so that's what's called the mean zero point Gray inequality. And for those of you who took my course in numerical analysis, we proved this in one space dimension previously. The proof is not hard to do. Now, you can also have a point Gray inequality if you add the zero boundary conditions to this space. But notice here that there's no boundary conditions associated to the space. We're simply saying we don't care what the u1 or what the h1 function is. This always is going to hold. This is called the mean zero point Gray inequality. So we might need this guy. So if that's true, then we can show that the semi-norm controls the h1 norm. Okay, the semi-norm controls the full h1 norm. So this contains the gradient part of the norm plus the L2 part of the norm. And the only way that that can be controlled is through some sort of inequality like that. All right. So by the way, in this case, if you have, so this function again, we're not assuming any boundary conditions associated to this guy. So we usually can't have an h1 norm control or semi-norm control the full h1 norm. But if I add or if I subtract off this average or this mean function, then I can do it. The mean zero point Gray inequality. Another inequality that turns up quite a lot, and one that we mentioned in chapter 6, is something called an inverse inequality. And this doesn't apply in infinite space dimensions. So this only applies for functions which come from a finite dimensional space, like VL. So if I'm looking at, oh, by the way, I want to mention that I added a new definition. So I want to introduce a second space called SL. So SL is the set of all functions VL that are globally C0, such that if I restrict VL to be to a triangle in the mesh, then I get a piecewise polynomial of degree 1. So P1 function. Let's see, do I put the superscript or subscript? I can't remember now. I'll put a subscript. So I'm going to use SL if there are no boundary conditions specified, and I'm going to use VL for that subspace of SL where when we restrict to the boundary, we get 0. All right, so this is a new space that I've introduced, and the only difference between SL and VL is VL is 0 on the boundary, and SL is not necessarily a 0 on the boundary. So sometimes it's nice to make that distinction between these functions. So this inverse inequality only applies for functions from either one of these two spaces. Now, the key idea here is that both of these spaces are finite dimensional. They're not infinite dimensional spaces. In fact, we can't really do computations over infinite dimensions with a computer. We need some structure which is a finite dimensional object. And so whether it's this space or this inverse inequality holds true. And so what we're using or what we're doing is we're estimating the size of what's called a heavier norm with a norm which is lighter. And what we have to do is if we do such a thing, we have to pay the price of an HL. HL is the size of the triangle K in this case, all right, to possibly a negative power. So let's try out a couple of things here. So let's suppose that we use Q equals, what happens if we use Q equals 2? So now what that's saying is we're trying to control an H1 norm with a lighter L2 norm. So we can do that as long as V is in a finite dimensional space, but we're going to pay a price, and the price that we're going to pay is going to be some negative power of H. Okay, so HL, and now let's put in the numbers here. Let's suppose we're in D equals 2 space dimensions. And so now we just follow the prescription here. D is equal to 2. So this is going to be minus 1 power and plus D over 2. So that's plus 1 minus 2 over 2. Okay. And that's going to be V in the L2K. So let's just figure out what power we have. So we have minus 1 plus 1 minus 1. So ultimately we have HL minus 1 power. This is what's called an inverse inequality. And the reason it's true is because all norms on a finite dimensional vector space are equivalent. All norms on a finite dimensional vector space are equivalent, but whenever we try to replace this norm with a norm like this, we have to pay the price of an H. And this is what's called an inverse inequality. This holds for any function from this finite dimensional space. Now remember, this particular function is just, when I restrict it to a k, is just a linear function, a linear polynomial function. The next estimate that I have is for what we call let's see, what is the correct terminology for this? I'm I know what the terminology is. It's usually what's called an embedding, all right? So now what we want to do is see if I can control an L infinity function by an H1 function, okay? Well, it turns out I can't do this in I can't do this in one dimension, or sorry, two dimensions, if I have a usual function. So for example, if I have a function that's in H1, so suppose that I have a generic function in H1, that's an infinite dimensional vector space, and I want to try to find a constant so that I can control the size of the L infinity norm, the maximum norm, with the size of the H1 norm. So the question is, can I do something like this? And the answer is no, you cannot. You can't do this. This fails. I can't find some generic constant C where this always holds for all functions in H1. Now, but you might say, well, okay, I need an estimate like this, but not necessarily in the infinite dimensional space, maybe only the finite dimensional space, VL or SL. Well, then it turns out you can do this. For example, if V is in VL, remember this is the one where I have homogeneous Dirichlet boundary conditions, then the L infinity norm of VL can be controlled by the H1 seminorm and a constant, but you also have to pay a price of some value of H. Okay. Now it's a weak dependence on H. It's only a logarithmic dependence on H. So it's not quite as bad as this inverse dependence that I had whenever I was trying to replace an H1 norm with an L2 norm. But if I really want to control an L infinity norm with an H1 semi-norm, then in general it can't be done. But for finite element functions, it can be done at the cost of this logarithmic dependence on HL. Now once again, if I'm not in this space where I have zero boundary conditions, if I don't have any specification of the boundary conditions, then I have to put the average back. And so I'm going to do this in a sort of what's called a local sense. I can show that VL minus its average, which is computed down here, in the L infinity norm, only on one triangle. I can do this on a larger set, but I'm only going to do it on one triangle. Can be again controlled by the H1 semi-norm, but at the cost of paying this this price of this logarithmic dependence on HL. Okay, so that's a cost that's not too bad again because the logarithmic dependence on HL is kind of weak. Now, why did I have to add the mean zero? Why did I have to subtract off mean zero there? That's because there are no boundary conditions associated to this guy. So I can think about it again like this. Suppose that this was a constant function and this was not there. Would this still be possible? The answer is no, because if it was a constant function, let's say this is equal to 1 million, then the maximum of 1 million is 1 million. How can that possibly be controlled by this number times this? Well, this is, remember when we compute the semi-norm of VL, that's the gradient of VL. And so the gradient of VL, if VL is equal to just the number 1 million, is 0. So this is going to be a constant times 0. So that's just 0. How can 0 be greater than 1 million? Can't be. No, it just doesn't work. So that's a tip off to me that I have to add in this. I have to subtract off the mean in order to get it. So this is the mean zero version. Now I'm going to need a lemma that follows from this last complicated estimate here. And so here's the lemma. Suppose that I have VL in SL. So the way I want to think about this is SL is gotten by refining the elements of the previous mesh, or in other words, this is a function on a fine mesh. And so what I do to get that is I take something which looks like this, say a triangle, and I'm going to refine it a couple of times. So I take that, and how do I do refinements? You take the midpoints of all edges, you're going to connect them, and let's do that a couple of times. Let's see. Let's see, do I got it? There we go. So now this object here, this might be what I could call a KJ. So that's a triangle in my course space. Okay, so notice that J is down here. And in my find space, I'm going to have triangles which are really small. And those triangles I'm going to call KL, right? So I'm starting out by assuming that I have a function VL in SL. So it's a function that is defined on triangular meshes that which look like this. Okay, it has fine bits of information. All right, and what I'm going to try to show is an estimate of the following form: it's VL minus VJL over the triangle KJ. So that's this triangle here, right? And so remember I said before, you can't expect to be able to do this because there's no boundary conditions on just one given triangle. However, I can subtract off the mean. And that's the same thing that I'm doing here. It's just subtracting off the mean. And previously I subtracted off the mean for this triangle. What I need to do is I have to subtract off the mean calculated with respect to the bigger triangle KJ. So that's that mean right there. So I'm taking the L function, which is defined on these little triangles. It's piecewise linear over those little triangles, but I'm calculating the mean on the larger triangle. So I hope you get the distinction. That's less than a constant times the square root of 1 plus log hj over hl, absolute value. A similar thing to what we had previously. It's just that now I'm getting two scales instead of one. Here was only one scale. Now I'm getting a ratio of two scales. The size of this mesh, which is basically the size of that triangle, HJ, and the small size of that little triangle, HL. So that's the fraction I need to calculate for that. Times the H1 seminorm of VL over KJ. So the H1 seminorm is the norm calculated over this big triangle again. That's that guy there. All right, so what I'm saying is there's some constant where we can do this. And the proof is an exercise that I'll leave to you guys, and it uses some of these theorems and lemmas that we've introduced previously, and especially this guy right here. Okay, once you know that, then you should be able to show this. In fact, all the structure is pretty similar there. Okay, so I have everything in my pocket that I need in order to get started. I'm going to need one more technical lemma before I can prove the first estimate. And the first estimate is going to be this guy here. Okay, so I have the couple of technical lemmas out of the way. I have one more to go, and then I can prove that guy. Let's see right here. Okay, so let's prove this technical lemma. Suppose that I have a polygonal domain in R2. This analysis, by the way, only works in R2. Let's see. So I should emphasize here, this is just for polygonal domains in R2. Such an inequality doesn't hold in R3. So it just doesn't work anymore in R3. And I have to abandon this analysis. So suppose I have a polygonal domain in R2. Suppose that IL is the standard Lagrange nodal interpolation operator from C into VL. And I can operate on any continuous function, and I can push that continuous function into the space VL, and I can choose whatever VL I want. I can choose all the way to the bottom, which is V0, or all the way to the top, V capital L. Okay, so any one of those spaces and anything in between. Now, for to make things sensible, I'm going to also define I minus 1. And the only way I can make sense out of I minus 1 is I can just say that's the zero operator. Okay. Then for any UL in capital VL, so this is the function that I'm looking for ultimately is going to be my finite element solution in the finest space. IL minus UL minus IL minus 1 UL. So this is the difference between the interpolation operator pushing this into space VL and the one that was just pushing it into space VL minus 1. So these should be fairly close to each other because the spaces VL and VL minus 1 are fairly close to each other, right? I'm going to measure that difference in the L2 norm, and I want to show that that's less than C times HL plus 1, or sorry, times 1 plus square root of capital L minus little l times the H1 seminorm of UL. Remember I said that this stuff gets pretty complicated. All right, so let's see if we can figure out how to do this. So once again, we start with something which is fairly coarse. So this would be UL, and I'm going to refine that a bunch of times. So remember what refinement does. So I take that guy, connect midpoints, and I need to take all the midpoints there, connect those guys. See, did I get that one there? And okay, so that's two refinements. So this guy here might be called KL, and this here would be what I might call K capital L. Okay, now I'm imagining there's a arbitrary number of levels between these two guys, maybe 5, but here I've only drawn 2. So I have this function which is defined with respect to this really fine mesh, but I'm going to do some analysis with respect to this coarse mesh. Okay. So the reason why I'm going to do the analysis there is because I'm projecting down to this guy, okay, this triangle in that space. So I'm going to define a piecewise constant function for this fine grid function UL L, and I'm going to define it in such a way as that, so it's piecewise constant. So the way I do this is for each k in the coarse mesh, that means coarse mesh, I'm going to just take that to be the average over that coarse mesh. So now remember, this function is really fine. It's got a lot of intricate details. It's a piecewise linear function over these triangles here. Okay, so that's UL, but I'm going to calculate its average over this this triangle K. So I chose not to call it KL, but I guess I could have. You can put an L here if you want L there. Okay. But in any case, you're choosing to calculate the averages over these fine level triangles, or sorry, these coarse level triangles. Okay, so now we want to do the estimate. Okay, so put this guy in your pocket. Once we get to triangle KL, I'm going to pull this guy out somehow. All right, so let's start by looking at the thing we have to estimate. Now, look at UL and L minus 1. Suppose I take this function here and I calculate its nodal interpolant at level L. And then I take the nodal interpolant from level L to level L minus 1. That's exactly the same as if I take the original thing, okay, the original function, and I push it by a nodal interpolation into level L minus 1. So the fact that I have an intermediate step here is no big deal. But now notice that what I have is something which looks like an error estimate or an error computation of a standard form. This object here and this object inside are exactly the same. They're the same objects. Okay? So that looks like object minus the interpolant of object. All right, so it fits into the form that I usually seen previously of VIL minus 1V measured in L2 norm. Well, that's just the error between a function and its interpolation into mesh into the L-1 mesh. All right. Well, I have an interpolation error estimate for that, and it's if I'm measuring an L2 norm, of course I've got a square here, then that's going to give me a first order error when I measure the error relative to the H1 seminorm. So first order means I get an H to the power 1, but because I'm squaring it, I end up getting an HL to the power 2. So that's the first estimate. This is just nodal interpolation. Okay, interpolation error. Interpolation error. So put that in your pocket. Now, what about this guy? Now, I'm going to squeeze in here this piecewise constant function. Now, notice that I'm summing over triangles here. I did two steps at once. I broke this global estimate into a local estimate by summing over the triangles, each individual triangle K in the mesh TL. Why am I allowed to put this piecewise constant function in there? Well, on each TL, that's just a constant, but when I hit this with the H1 norm, remember H1 norm means the L2 norm of the gradient, but this has a gradient which is equal to 0. So I've added nothing at all by putting in this piecewise constant function. That's why I have this equality there. Okay, I've added 0 because the gradient of this function is just 0 on every triangle. Right now I can apply 6, which is that estimate that I had controlling the H1 norm by the L infinity norm. So that was with what we called the inverse inequality. So if you go back to 6, that was my inverse inequality. I'm going to try to control H1 with L infinity. That means Q is equal to infinity. Am I allowed to do that? The answer is yes. I can go all the way up to Q equals infinity. When I do that, I get 2 over infinity. That's just 0. And I get 2 over 2. So it's 1 minus 1 plus 1. That just gives me 0. So I'm allowed to control H1 norm with L infinity norm, no problem. But now I've got to find my way back. Let's see. Okay, so that's what I did there. Now the next step is I'm going to pump this guy up. So remember, this is a nodal interpolation of some fine grid function. So that fine grid function has a lot of stuff going on it. But what I've done here is I've replaced that by its nodal interpolant at some coarse grid points. So basically I'm replacing it by a function which is like this blue curve that I just drew here. Well, that's a piecewise linear function, but on a coarser mesh. It turns out, it's not probably too difficult to see, that when I measure the maximum of this function, and actually the maximum of this difference, then I'm measuring it with respect to this function here. That's this guy. But what about this guy here? It has many more peaks and valleys. In fact, it matches only at these endpoints. The maximum can only get larger if I replace this interpolated function by its original function. So that's why I can replace that interpolant with the original function, because the infinity norm is only going to get larger by doing so, replacing this by its original function. That's because I've destroyed a lot of information by doing that replacement. Okay, so replace this with that, you get that inequality. The next step is, well, applying that technical lemma that we just derived. Okay, so, well, we didn't derive it, but that technical lemma is the one which I said was going to be an exercise. Remember, it's done over multiple scales, and so you get this log of the two scales, HL over H capital L. All right, so that's the technical lemma that we didn't prove, but I said is an estimate that you guys can do as an exercise maybe later on when you're feeling really bored over the holiday break. Okay, so that's the estimate that I wanted. And so right now, what can how can okay, so now this guy here can just be brought out front because it's the same for every triangle. Okay, there's no triangle dependence here, so I can bring this guy out. But I'm summing the L2, or sorry, the H1 seminorm squared over all triangles. Well, that just gives me the H1 seminorm over the full domain. Okay, and with this constant brought out, the C and the HL squared were already there, so I'm just going to leave those there. Okay, to finish this off, all I have to do is make a couple of observations. So the observations are the scale of HL, that's like H0 times 2 to the minus L, and that holds true for all L between 1 and capital L. Okay, in fact, it even holds true for L going down to 0. So that means I can calculate this ratio. When I calculate the ratio, HL over H capital L, that's just going to give me H0 2 to the minus L over H0 2 to the minus capital L. H0s cancel, right? And so I just get 2 to the L over 2 to the L. And then if you take the, and of course this is just equal to 2 to the L minus L. And if I take the log of that, then I just get L minus L log 2. And that completes the result that I wanted to show. Okay, so that's all the key technical lemmas out of the way, and finally we can go on to prove this result. So how do we do this? Well, this one is again fairly technical, but it just uses the technical theory and lemmas that we just proved to put everything together. Again, it's a little bit complicated, so try to pay attention to the steps. But if you miss one or two steps here and there, it's not a huge deal. I do want you to pay attention to see, if you have any questions, let me know. But if you spot any errors, of course, let me know that, or if something just doesn't make sense and maybe I'm assuming something that I shouldn't. Please let me know. Okay, so, oh yeah, this guy here, I think I would add, this is not a typo, but I think I might want to add here that each one of these functions are in WL. Okay, so I want to show that the minimum eigenvalue of this matrix, and of course this is a typo here. I need to go do a global search on that. So BH, I'm no longer using B. Remember, I banished that. It should be CH. Okay. And let me just go back and make sure I have that in the previous. Yeah. See, it should be CH, CH, CH. Okay. So I apologize for that error. Should be CH. All right. So we want to show that the minimum eigenvalue of the preconditioned matrix is greater than constant C1 over 1 plus log HL absolute value squared. Okay, so let's start off with two arbitrary functions from WL. Call them WL1 and WL2. Remember, we defined this bilinear form, CL. And how do you define CL? Well, you take two functions from WL and you plug them in, and the definition tells us, well, we're going to sum the values of those functions at the nodal points of W, okay, from 1 to ML. That is the number of nodal points in WL. All right, so that's how we define CL. And remember, we build a matrix from that, and it turns out that matrix in the canonical basis is nothing more or less than the identity matrix. Now we're going to let WL alpha be the coordinate vectors for each of these two finite element functions. Remember, this is what I mean by finite element functions. No boldface, no vector on those guys. The coordinate functions, or the coordinate vectors, are bolded, and they're each from RML. They're connected to those functions through the basis BLW as usual. So now the So if I look at this operation here, let's try to understand what that operation is. CL, WL1, WL2, those are two vectors, and I'm measuring those in the space or in this inner product from ML. CL is the matrix just equal to the identity, okay? So all we do is, so how would this be defined? This is just going to be sum I equals 1 to ML of the coordinates for these two vectors summed up. But now the coordinates of these two vectors, by definition, are related to these functions from the finite element space, and precisely, they're just the values of the finite element functions at the nodes of W. All right, so remember there are exactly ML of those nodes. So that's nothing more or less than CL inner product of WL1, WL2. And of course, I can interchange these two without any problems, right? Because this is by definition CL, and it looks like order doesn't matter, so I can interchange them. So that's all I'm showing here is that order doesn't matter. So I can define this object here to be equal to that. And that's nothing more than an inner product, okay? And it looks like what's called a mass lumping inner product. All that's missing is a factor of HL squared. Okay, this is a little bit of a typo there. It's a typo because the square should be further back. Okay, so this we showed in chapter 6. Any object which looks like that can be related to or is in agreement with an L2 inner product or L2 norm. So we showed this already in chapter 6. If you have some object which looks like this, then it's intimately related to the L2 norm or inner product. And therefore, what we can show is that there are these constants C3 and C4 so that I have this norm equivalence. So this is a norm, this is L2 norm, and these are the two norm objects. These are, well, norm squared for this object here that I just demonstrated. So this object here, I didn't show specifically is an inner product, but it's not hard to conclude that because of this statement here, because we know of that form. Okay, so it's equivalent to the L2 norm, and this is basically by work that we did in chapter 6. So now I can either use this object here, that's a norm squared, or I can use this object here, that's also a norm squared. So either one of those two objects can be used. All I have to do to get this equivalence right is insert this HL squared. And the reason for inserting that HL squared in 2D is because basically, if I think about this as point evaluation, this is somehow like the two-dimensional trapezoidal rule, which requires an HL squared. And again, I don't like how that is not hugging that thing there, so I'm going to fix that. Okay, so the exponents are fine. It's just they should go closer to the H. Okay, so continuing on. So let's again look at this object here that we just created. Okay, we know that it's related to this object, which is equivalent through the proper equivalence coefficients to the L2 norm. Okay, so that object we're starting with the vectors and the norm, that's just the identity norm. That's equal to this object here because of our definition. Notice that I've just multiplied and divided by HL squared. And now if I go back to 10, I already showed how this was equivalent to the L2 inner product, but I can just restate that there. When I change from this norm to this norm, I have to pay the price of a constant and a power of h. Okay, so that gets rid of this guy and introduces that constant. what about the next thing? This next object is a little bit weird, and it took me a few minutes to figure this out or rediscover what was going on. Why can I replace this with a quality? Well, WL is what appears there already with L2 inner product. That's all the same. All this is the same. So basically, all I've done was introduce this minus here. The reason why this is equivalent is because this is identically equal to 0. And the reason it's identically equal to 0 is if I take a WL function, remember WL functions are functions which look like so, right? Every other node, they're equal to 0. So what happens if I take their interpolant at the level L minus 1? Well, that would be its values at these nodes where it's 0, okay? Precisely equal to 0. And so that's why it's equal to 0, because you're interpolating onto points where the degrees of freedom are already zeroed out. It's a little trick. So now, however, it looks like it's voodoo, but it helps with analysis quite a bit, because now I look at this object and I say, well, this looks like an interpolation error, right? Original function minus its interpolation at into some mesh of that same function. And so if I use my interpolation error from chapter 6, that says that this is going to give me an order 1 error, but it's order 1, but I'm squaring it. So I get an HL squared, which cancels that guy. The extra coefficient comes because that's my interpolation coefficient, and I'm measuring in the H1 seminorm, this original function. Okay, so that's what happened to this HL. It got canceled out because of the interpolation error. Now I'm going to try to estimate a heavy norm with a lighter norm. And if I do that, then I have to use an inverse inequality. So 6 is my good old inverse inequality. This can only be done for finite functions from a finite dimensional space. And the price I have to pay there is, when I go to the lighter norm, I have to pay the price of the singular value of HL, HL to the minus 2 power. And then finally, I can use 10 once again. 10 was my equivalence between the L2 norm and this object or this object, either one. And when I do that, I gain a power of HL to the 2, or to squared. And so once I gain that power, I have no HL here. I gain an extra C4, but now I'm just going to take all these constants and just mush them together as one constant. So what did I show? This is less than a constant times that. That seems like a pretty stupid estimate, right? But actually, there's much more to this estimate than meets the eye. So I'm sandwiching this object between another object of the same form and then this object in the middle. And so what I'm showing is essentially the H1 norm, and these objects here and here are equivalent. Okay? So I showed that for WL for some L, but I can now sum over all of these WLs. Okay? And I can get an estimate of this form. Okay, so bear with me. We're almost done with this estimate, and then we'll be done for the year here. We won't quite make it all the way to the end, but let me at least get this finished off. So what we've just proved is this equivalence here between the H1 seminorm, when I sum up all these functions from the various WLs, and this guy which sits in the middle. Okay, so this holds for any collection of WLs where each WL is in these capital WL spaces, these hierarchical spaces. Now finally, let UL and VL be given. And what we showed in a previous lemma, or at least you would show, is that we have the subspace decomposition of UL into WLs. Okay, so in fact, we know how to do that. If I just break WL into ILUL minus IL minus 1UL, then that gives me my each individual WLs. And each one of these guys is in WL, and so it all works out. Now, if we make the usual identification of the vector with the function, then what we're basically saying is that if you remember back in the slide deck 1, that this collection of function is in the Q class of UL. All right, so now I'm going to skip through the details here because of to save some time. So what we're going to show next is that this is less than this estimate here, okay, where we're taking the sum over the full space. This is the H1 seminorm, UL squared. Now these WLs are connected to UL through this Q class, or in other words, this subspace decomposition. And then what we're going to do is try to convert this guy back into something that we can deal with. And it is nothing more than ALULL. And we want to convert this object into something which looks like a logarithm. So I do that through this estimate here. And when I put everything together, what I've just proven is that this sum is less than this coefficient times a constant times AL. This is missing an L here. This should be A sub L, U sub L, U sub L. Now that's it. Now it follows from a big theorem from the last slide deck that the lambda min has to be greater than the constant C1, some constant, and we're going to use this as our constant, 1 over or 1 plus log HL squared to the minus 1 power. Now, what big theorem is it that we're using? Basically, we just received an estimate of this guy in terms of something which looks like the original ALULL inner product. And this is the big theorem from the first slide deck that we're using. And this is the estimate that we're using here. So basically, we just got a lower bound estimate, or no, it's an upper bound estimate of this guy here. Now, these WLs are certainly in the Q class because they were constructed such that that was true. So now when I replace this guy by replacing this by the lesser value, what I get is a cancellation of this with this, and all I'm left with is this estimate here. So the details I don't have time to go through because I've run over, but once you get this estimate here, then this estimate follows for free from this big theorem that we proved in the first slide deck. That's where I have to stop. So the next estimate would be putting things together to show that we've got a lower or an upper bound on lambda max, which looks like this. And simply don't have time to go through all that. We'll do that next time that we meet. And the next time that we meet is going to be next semester. So we'll pick up with hierarchical basis in the next semester in January, and then talk about the BPX preconditioner. After that, we're going to go into chapter 7, when we'll talk about multigrid methods for cell-centered finite difference approximations. And after we do chapter 7, we're into chapters 10 and 11, where we're talking about, again, subspace decomposition methods for solving nonlinear problems. Well, I'll stop there, and you guys can turn your cameras back on, and I can take any questions you have.